Okay, a loop or wire. A loop or wire. A loop of wire. Where the radius of 0.9 meters is in the plane of this page and is rotated so the loop forms a 42-degree angle with the page. So it's in the plane of the page and then it's rotated. So let's draw a picture of this. Okay, so here it is in the plane of the page and then it is rotated so that it's 42 degrees. I'm trying to draw 42 degrees. Right, so it's rotated from here to here. So let's see, and the magnetic field is definitely into the page, right? So if this is the page, we're looking down at the page from below. Let's draw a little picture. Cyan was always a good color here, so. Okay, so here's my magnetic field. All right. So this is my magnetic field here, right? Is into that page, right? All right, and so what's happening here, I believe, is that we are losing flux into the page. We lose flux into the page, and so what we're going to do is we are going to, if we lose it, we replace, right? We'll replace flux into the page, and the way to do that is to go clockwise, right? Because clockwise creates flux into the page. Creates flux into the page. And then this is going to end up being, EMF is going to be the change in flux, right, over time, which is NBA cos theta, right, divided by time. And what's happening here is that the angle is changing, okay? So it's not the area, it's not the magnetic field, it's not the number of windings, right? It's that is changing, right? And then the question is, do we have the right angle? Well, I think we do. I think this all works because remember that magnetic flux is actually at right angles to this, right? But that also works, right? If this is 42 degrees, yeah, this will work. Okay, we're in good shape. Okay, so let's see. So this is one winding. Magnetic field is 5.73 teslas. Area is, it's a loop, it's a radius. Oh, what if there is, what time? Oh, we're trying to find the time. Oh, 0.9 meters, so pi times 0.9 squared. All right, and then EMF, we know what it is. It's 16.7 volts. And then T is what we're trying to find. And then let's see, this is going to be cos 42 minus cos 1 or 0, right? Okay. Notice that the net effect of this is that it's always 1 minus something or something minus 1. There's also a minus sign in here that we're just kind of ignoring because we know that it's going clockwise. So if I get a minus sign, I'm just going to kind of ignore it because I already figured out the direction. Okay, so 5.73 times, oh wait, what do I want to do? Actually, yeah, I want to do this and then divide by 16.7, okay. Times pi times 0.9 squared times cos 42 minus cos 0, which is 1, right? And then I want to divide that by 16.7. Is that right? And I get 0.224 seconds. I get negative 0.224 seconds. Remember, we're ignoring that minus sign. Or I could slap a minus. I mean, it really doesn't mean anything. The minus sign on there is not useful to us in any way. There we go. All right. And then, if you're all happy and good, you can stay on there. We could also look at the direction of this magnetic field. Really, the angle between the magnetic field and the area, if we say the area is up like this, right, that angle is here, actually 180 degrees, right? which doesn't really matter, right? The final one is 180 degrees. Oh, wait. The initial one is 180 degrees. And then if we look at this one here, that's 42 degrees. This is 42 degrees, right? And so the new angle twixt the area. Remember, area is a vector perpendicular to the area, right? The angle twixt that is, what is that? It's 180 minus 42. Way too slow, 138 degrees, right? Okay, and this also works, right? If I go cos 138 minus 1, I'm sorry, minus cos 180, I get that, and if I go cos minus cos 0, I get exactly the same thing. So one's positive, one's negative, but again, we divide, we ignore the minus sign. So, all right.